Hello, everybody. Welcome to the World of Control channel. I'm Mohammed, and today in this video, I want to design a PID controller for the inverted pendulum system that we modeled it in the previous video. Uh, okay, for designing a PID controller, we use this control law here. We write the control input tau as a function of the error of the states. And we defined the error uh, like this, and we want the angle of the pendulum to be theta desired. So we calculate the differences of the theta desired and theta dot desired from their actual signals and uh, write the errors like this. And after that, we use this control law to control the system. In this equation, K, P, KD, and KI are positive and constant. Okay, let's model it in the Simulink. Okay, this is the simulation that we did in the previous video. I will delete this constant here, and I want to um, design a PID controller now. One of the benefit of the Simulink and MATLAB is the applications and the strong functions that MathWorks built for the Simulink and uh, MATLAB here. Okay, so there is a block in Simulink library called PID Controller. Sorry, I will import a PID controller here, and now we need to calculate the error of the uh, angle. So I import a constant to be the theta desired, and for example, for now we want to regulate the system on pi divided by 2. Okay, we apply this. Okay, and now we need a sum reshaped it to the rectangular, and we need a plus and a minus here. Apply it. Okay, this is pi divided by 2, and this signal should be the theta signal here. The input of the PID controller block should be the error. This is the error, and the output is tau. Okay. For a better comparison, I will import a mux block here, and I will import the reference signal from here to the first figure here. So we can compare the two signals, the desired signal and the actual signal. Okay. Now we need to regulate the PID coefficients. So we go to the PID controller block and we choose PID, and after that there is a tune button here that I will click on it, and the Simulink will automatically design a good controller for our system. Okay, Now we can see that the controller uh, this, is applying to the system, and the PI and D coefficients are written as shown here. We have some scroll bar here that we can regulate the response time or transient behavior here. For now, it's okay. From this icon, we can see the PID parameters, the values, and the properties of the tuned system here, such as rise time or settling time or overshoot. And we can regulate these scroll bars to change in these properties here, so we can obtain our desired situation and desired circumstances. Okay, with this run icon, we can update our block. I will click on it and close the PID app. So now we can see that the coefficients are tuned and as their appropriate values. So I click on OK and I will run the simulation. Okay, I think something is wrong here. Let's see. For 25 seconds, we run the code. Okay. There's something wrong here. We have to see the signal regulated on 90 degrees. So let me find the problem here. Okay. Let's start from 0 and let me check the equations. Tau is tuned or not. Let's again tune our parameters. So I will click on the tune button again and let's see what we have. Okay. Oh, now I think it is correct. So we can have the correct coefficients. So I click on the update block here, and now we can see the results. Yes, the coefficients are updated. So I'll click on OK and run the simulation. And now, yes, the system is controlled on the 90 degrees here. So let me reduce the stop time here so we can see that system is controlled on 90 degrees. Now I want to investigate the effect of the disturbance on the system. So first I will import, for example, dist here to the dynamic block, and I will add a disturbance as dist here to the equation of motion here. So we will import a random number here that is represent as the disturbance. So I will reduce the sample time to 0.01, and I will increase the variance to, for example, 300 here, and with the mean of 0, and I will apply this to the system as disturbance. And now we want to see the robustness of our controller with the existence of the disturbances. Okay, now I run the simulation to see if the controller is doing well. Okay, now we can see that the controller is robust, uh, and we can see that actual um, the actual signal is controlled on 90 degrees, but we can see the effect of the disturbances on this actual signal. But we see that the system, the controller, is doing a good job here, and the disturbances are damped, and um, the controller is doing a good job. In the next video, I will design a different controller for our system. Thank you very much.